Hi everybody, today we're going to talk about linear programs following the next course part of the Columbia course. Okay, so what is a linear program? A linear program is an optimization problem where you're trying to maximize Ct of x given that a times x is less than or equal to b. So again, this is maximize Ct of x given that ax is less than or equal to b. So Ct is it's transposed, so it looks like this. It's a matrix like this. So let's say n by 1 or whatever. And then this is x. It is a column vector. And so that's that. And then we have A over here. A is a big matrix, not necessarily square, multiplied by x. And this is supposed to be element-wise less than or equal to b, which is another one here. Okay, so let's go over an example that was given in the course. So suppose you have, I think it was like D stocks. And so then at t equals 0, you purchase some of them. So the problem, let me just say it's called a hedging problem. Hedging problem. So at t equals 0, you purchase some of them. And the idea is purchase some of them. The idea is that at t equals 1, you're going to liquidate them, sell them at a market price to cover some cost x. So there's lots of, so at t equals 0, the prices are known. So here's prices are known. But at t equals 1, a lot of things happen. So you get, so these are all possible different things that might happen at t equals 1. A lot of it's random, right? A lot of random things might happen. So like maybe you bought a stock and its price dropped to 0. So now it's worthless, right? Or you need to cover a much bigger cost than you expected, right? Both these things are random. So x, so at time equals 1, so x, you need to pay x, and then the stocks change. Okay, so I feel like I'm going a little bit too far away from what a linear program is. Let's just say right away. So this is the, so in this one I did max Ct of x, ax less than or equal to b, but there's also a linear program min of Ctx, ax is greater than or equal to b, which is the one that we're going to go down here. Okay, so in this case, let me just rewrite it. Ct of x, given that ax is greater than or equal to b. So C in this case is the price of the stocks. So again, it's a vector at t equals 0. So you want to minimize the amount you pay at t equals 0 to hedge, right? Then x will be the number of stocks you buy for each stock, number of stocks you buy. So if that's true, then Ct times x is the total amount you spend of money to hedge, right? And then A will be a matrix like this, S1. So this is a row. Each of these S's are rows to S probably D, where S1 is, so let's see, we're multiplying it by X here. Oh yeah, I should also, I guess it might be easier to think about what B is here. B is this thing, so it's the amount that we have to cover at t equals 1. So B will be the amount to cover at t equals 1. Okay, so then now that we know this, it becomes very clear what S1 is. So S1 is, so here we're multiplying it again by the number of stocks to buy. So this is how many to buy of this one, how many to buy this one, how many to buy this one, how many to buy this one. And again, this is a optimization problem we're trying to solve. We're trying to find the optimal value of x to minimize this c t of x. So there can be lots of different values that work, but it's like a whole plane of possibilities. But we're trying to find the minimum. Don't know where I was going with that, but okay. So then S1 here, SA. So S1 is for stock 1, it's like across all realizations. So it's the price of the stock at t equals 1 for all model realizations. So let me again back up to what the whole model is. So we start at t equals 0, we have prices for the stocks, and then at t equals 1, a lot of things change. The stocks change, and we have to cover some amount of money that we need to pay by liquidating everything that we bought. So we need to make sure that our solution works for all possible models that we predict might happen. So maybe the stock market crashes and one of our stocks goes to 0. We need to make sure the other stocks are still performant enough to cover, right? Or maybe, you know what I'm trying to say, or maybe they all go up, but we have a lot to cover in that case. We have a lot to hedge. We need to pay a lot, which is why it's an optimization problem. We're trying to find the right amount of stocks to buy that in all cases, in all possible future situations, we're going to cover our required amount. Okay. So yeah, hopefully that makes sense. So then I want to talk about the dual of a linear program. Okay. So the dual of a linear program is also a linear program. It's very related to the original linear. So you have a linear program. Let's just say ct of x, ax less than or equal to b. And again, you're maximizing this in this case. The dual of this particular linear program is b transpose y, where a transpose y is greater than or equal to c, right? So you can see this thing here moved over to become our constraint, and then this thing here, the constraint, became the thing that we multiply by. And it turns out these two linear programs are very related, and actually you can prove that there's something called weak duality, which says that this is true for any linear programs, that the maximum of in this case ct of x, which we'll call d, is less than or equal to p, which is so basically the solution of the first linear program is always less than or equal to the solution of the second linear program. So that's called weak duality because there's a less than or equal to, bt of y. Now strong duality is actually that if either p or d are finite, meaning they're not equal to negative infinity or positive infinity, then p is actually equal to d. Okay. So I guess to have an understanding of what p and d is, I'm going to go over another example of a linear program taken from Wikipedia. So in this example, you have a factory that is producing goods. Factory producing goods. So let's just say So we're trying to maximize the amount, the total money we can make by producing goods. So C in this case will be a vector like this. It will be the prices of the goods that we're trying to produce. And X will be the number of goods we're trying to produce. So this is our thing that we're trying to optimize for. We're trying to get the best configuration of X that we make the most amount of money. Okay, and then we have this A. So in order to produce goods, we need raw resources. So here's our A, and here's our X. Again, this is the number of goods to produce. And then we're constrained with our factory only has, let's say, B number of goods. So here's good 1, and we only have this many of good 1. Of not good 1, I meant, sorry, raw material. So we only have this much raw material. So this is our constraint. So then, in order to produce good 1, we need this much raw material, and then in order to produce good 2, we need this much raw material, and you can see that it multiplies, right? And then we go to good n. So you can see, so this column right here is the all the different materials we need to produce good 1. And again, we're trying to maximize the amount of money we make. Okay, so now let's talk about the dual problem. The dual problem is this: minimum of B transpose Y, where and then again I'm going to draw this out. So like this. And then we have A transpose. So now we will have good 1 on top here because we've transposed it, good n. Then we have this mysterious Y that we haven't talked about yet. And then we have Y, 1 to Y. It's not going to be n, it's going to be D because it's transposed. And then here we'll have greater than or equal to the prices. Okay. So here is the understanding of what the second of what the dual of this is. And by the way, I should mention that the dual of the dual, so if we call the first this first problem equal to the primal, then this is called the dual linear program, and then the dual of the dual is the primal. You can show that if you do the exact same process, you end up with a primal, with the original linear program. Okay, so let's go back to this example. So here we have our, let me see, I'm still recording, yes, okay. So here we have our prices. So what might this mean? So as discussed by Wikipedia, we have in this dual part, we have a second factory that doesn't have any raw materials at all. So it needs to purchase all of its raw materials. So this is and it can decide how much it's going to pay for those raw materials. So this Y is going to be the price it wants to pay for the raw material. Price to pay for raw material. Okay. And then this B, if we go back to here, B is our constraint, how much raw material there exists. How much raw material exists. So it can it can only buy it from factory A, basically. And then it needs to do it in an intelligent way, right? If a good is super expensive to produce, you probably don't need that much raw material. Like, and it requires a certain raw material. You probably don't need that much raw material of that good because it doesn't make sense to buy raw material because you don't want to produce a good that doesn't make that much money, right? So you want to make sure here that the good, right, multiplied by. So here we have, I guess technically we can see like this will be, so for raw material, this, like, does it make sense to buy how much of it, or sorry, at what price to make sure that, right, to make sure that it's profitable, right? All right, it's a little bit difficult to explain, but you kind of see that it might work this way. Okay, so then I wanted to talk about, so there's a part in the second presentation where the professor discusses the construction of the dual. So I looked on Wikipedia and I found his explanation confusing. So I think we can just do it the old-fashioned way through Wikipedia. So let's take, suppose we have a linear program that's this. So we're trying to maximize this given that ax is less than or equal to b. Okay, so then ct of x, right? We can and again what we want to show is we want to show that the maximum of this is less than or equal to the minimum of b transpose y, where b transpose y is, you get it, b transpose y, where a transpose y is greater than or equal to. So yeah, we're trying to prove, again, prove at least weak duality is greater than or equal to c. Great. Okay, so we're going to start with this ctx. Then we are going to flip them because we can do that. xtc. Now, according to this, right, we have this is less than or equal to, according to this statement here, xt a t y, like this. Then, according to associativity of matrices, we have this is equal to, instead we're going to multiply these first two, y. And then according to definition of transpose, we have this, ax ty. And then, given that ax is less than or equal to b, this is less than or equal to b transpose y. And this holds true for all c and b. Therefore, d is less than or equal to b. And that's the end of our proof. Okay. So, so the professor, what he was trying to prove is he was trying to, I guess, sort of come to an understanding of where this y comes from. I mean, if we know that this this dual already exists and we define it, then we can already show, like I've just done here, that this dual is indeed, related d less than or equal to b. But I guess he was trying to provoke some sort of understanding of the construction. So something he was trying to, let's say, minimize. I think so in his, he was talking about b transpose y, and then another thing, often like when you're constructing the dual, you have to give a constraint that x is greater than or equal to 0 or y is greater than or equal to 0. If they're both greater than or equal to 0, this is called a symmetric dual. And if and then if only one of them, like if the first one and then you're constructing a dual from the second one definitely has to have the constraint, and when it does, it's called asymmetric. Okay, so then I think in his construction we do this where we this is greater than or equal to, and then we subtract off this weird thing here, a transpose, not maybe a transpose, like something like this, and then I don't know, then we relax the constraint, and then we show that something like that. Okay, great, thank you so much, see you next time.